Good afternoon, everybody. We're going to get started here. We've got an exam review question, since there's an exam this week. We don't really have time for a lot of review, so I've already posted a practice exam for this exam, Practice Exam 3. If you haven't seen it, it's in the course content folder. So check that out. It's a few questions. They're practice for the exam. It's not for credit, but it's there if you choose to use it to study. I'm going to go ahead and solve this problem, and feel free to chime in with your questions if you need to. If you didn't get a chance to start it or finish it, that's all right. Make sure you understand it. When 85 grams of methane are mixed with 160 grams of oxygen, the limiting reactant is, and you've got to choose. Well, we've got to do a little bit of math first. We've got two reactants, methane and oxygen. They combine to make products, carbon dioxide and water. What you want to do here is choose one of these two products to kind of complete the question. Because in order to figure out which one is the limiting reactant, you have to figure out which one of these reactants will make the least amount of product. And that's the real question that we're after. I'm going to go with carbon dioxide here. But you can use water as well. Doesn't matter. So we've got to do two mini problems. In either case, we have to go from grams of our reactant to moles of our reactant to moles of product. We need the molar mass of the reactant. So if it's methane that we're dealing with, we need the molar mass of methane. We'll also need the molar mass of oxygen gas. And that's going to take the grams and convert to moles. Then we need to go from moles of reactant to moles of product. That's where our mole-mole factor comes in. That is from the chemical equation. I'll do methane in black and oxygen in purple. Starting with the methane. You've got 85 grams of methane. The molar mass of methane, the way you calculate that is you take the atomic mass of carbon plus the atomic mass of hydrogen, but you want to multiply that hydrogen by 4. When you do that, you get 16.04 grams in 1 mole. Should have done this in red, my bad, y'all. So that's the molar mass of the reactant. Then we need a mole-mole factor. And this is going to tell us how many moles of methane for how many moles of, in this case, I'm going to choose carbon dioxide. We can write two mole-mole factors. I see 1 mole of methane. There's no coefficient, so that's a 1. There's no coefficient in front of the carbon dioxide either. I can also write the reciprocal. Which one of these do I need to use to convert moles of methane to moles of carbon dioxide? Right. So when I go through and do my unit analysis, grams cancel. I've got moles of methane. My moles cancel. And I've got moles of carbon dioxide. When you do the math, you should get 5.3 moles of carbon dioxide. But we're not done. We've still got to check out how much product we would make if we used all of the oxygen up. For oxygen, the molar mass is going to be the atomic mass of oxygen times 2. So 16 times 2 is 32. This time, we're looking at the relationship between oxygen gas and carbon dioxide. We've got 2 moles of O2 for every 1 mole of carbon dioxide. And then, of course, we have the reciprocal. Which one do I use? I use the same one, B. Both of them have the carbon dioxide in the top, and it'll cancel out the moles of reactant on the bottom. My grams of oxygen cancel, I get moles. My moles of oxygen cancel, I get moles of carbon dioxide. .5 moles of carbon dioxide is definitely less than 5.3. So that means oxygen is a limiting reactant. Any questions here? Yeah, so this is a limiting reactant question. Notice how both of those are on the reactant side. So when you have two reactants, you have to do them separately to see how much product each of them will make. Okay, well, if you want some more help with that, let me know after class. We can set up a one-on-one session. Yes. Okay. So that's it for Chapter 7. We've got to get all of Chapter 8 in today. And while we're at it, we'll talk about the exam. So Exam 3 opens today, right after class. We'll say 5 o'clock. And it closes on Saturday at 11:59 p.m. There's a practice Exam 3 posted in course content. You can use that to help you study. If you need a one-on-one session, you need to let me know right after class, and we can set something up. If you don't, then I can't fit it in tomorrow, because tomorrow is the only day I only have a couple of slots available. So if you need help, let me know. If you want to do like a group something or other, like, okay, there's a bunch of us that need some help with Chapter 7 stuff or Chapter 8 stuff, let me know. We have to organize it directly after class. If you send me a message tonight in course messages, my response is going to be, sorry, can't help you, didn't give me enough time. So think about it, figure out your life, let me know if you want some help from me. All right, so Chapter 8, all about gases. Hopefully you were able to watch the video. It's been up for a while. There's also a Chapter 8 check-in. Remember, that's for your participation grade. So there's a few questions on there to do. And hopefully between working through those, working through some practice problems here with me, Chapter 8 will be a breeze. We're not going to hit every single conceptual topic. If you have not looked at the YouTube video for the pre-recorded lecture, you absolutely have to, because I'm not going to cover every single concept. We don't have time to cover all the concepts and do practice problems for all the concepts. So I'm really just hitting most of the math, all of the math actually, and we'll sprinkle in some other concepts along the way. So if you haven't watched it, you really have to before you take the exam. So the first place we'll start is the first section. It's a good place to start, right? Talking about the properties of gases. We've got the kinetic molecular theory, which describes a gas. Small particles, they move randomly and fast. There's no real forces that act between them. Gases take up a larger volume than just the molecules alone. And we use a Kelvin temperature. So that's just a quick summary of the kinetic molecular theory. I don't have any questions surrounding this. This is something that you have to just know. And then with multiple choice questions, you should be able to recognize these pieces as part of the kinetic molecular theory. Any questions about what you're expected to know from this slide? I'm going to take that as a no. This table summarizes the properties of gases that you're going to be responsible for: pressure, volume, temperature, and amount. I talked about each of these in detail in the video. We're not going to go through them one by one. Instead, we're going to do some practice with pressure conversions, and we'll talk about each of these properties as we go through the different gas laws. This is a good summary table that if you need, kind of quick definitions or descriptions, this is the go-to. This is another really good table to keep for yourself. You're not going to be asked to memorize these, but it helps when you kind of have them on lock. You can look it up in your notebook. The main ones that you'll be seeing are the top three: atmospheres, millimeters of mercury, and torr. The others you may see, but they're not really used as much in chemistry. We'll be needing these numbers when we do all of our conversions. Notice that for the top three, atmospheres, millimeters of mercury, and torr, that their unit equivalents to 1 atmosphere are exact. When they're exact, that means that we don't take them into account for sig figs. So let's do some practice. I'll give you the equality that you need here. And we have two. Oh, I'm outsmarting myself. I already put it down here at the bottom. I forgot. Now you have it in two places. You have the first one, you're converting millimeters of mercury to atmospheres. The second one, you're taking atmospheres and converting to millimeters of mercury. So here's what we can do. Two choices. I can go over the first one and then I let you do the second one. Or you can work on both of them on your own for a couple of minutes and then I'll go over them. So let me know which one you want to do. You want me to go over one first, or do you want to be let loose to try it on your own? Okay, I'll go first. We have to convert 475 millimeters of mercury to atmospheres. I always like to rewrite the question. That's what we're looking at. We already know the equality. We can write two different conversion factors from this equality. There's one. And there's the other. We're starting with millimeters of mercury. which one should we use if we're trying to get rid of millimeters of mercury and convert to atmospheres? We've got the blue one and the purple one. If we need to get rid of millimeters of mercury, because they're in the numerator, we have to use the conversion factor that has millimeters of mercury in the denominator. That's going to be the blue one. We cancel those and we're left with atmospheres. You can try it in your calculator if you'd like. You're taking 475 and dividing by 760. It's B. Now, we could have done this one without even touching our calculator, and I'll tell you how. "475 millimeters of mercury." They're not equivalent, so it's not going to be 475 atmospheres. It's not that easy. It's not 1 to 1. Then you have 3.61 times 10 to the 5th atmospheres. Again, as long as you know 1 atmosphere is equal to 760 millimeters of mercury, that number doesn't even make sense. 475 is less than 760 millimeters of mercury, which means it's going to be less than 1 atmosphere. So the only reasonable answer is B. Would you like to try number 2 on your own, or do you want me to go over it? All right, then I'll give you guys about 1.5 minutes to give it a shot. You've already got the conversion factors right there. I'll check in about, we'll say, a minute. I'm going to let folks work on it a little bit, and then I'll chime in with the answer. Okay. As always, go through the problem, figure out what the question is. The pressure in a tire is 2 atmospheres. What is the pressure in millimeters of mercury? Start by rewriting the question. This time we're starting with atmospheres. So we need to use the purple conversion factor with the 760 millimeters of mercury on top, 1 atmosphere on the bottom. That way we cancel out the atmospheres. We're left with millimeters of mercury. And yes, the answer is B. This is another one that you can reason without using your calculator, as long as you know 1 atmosphere is equal to 200 or 760 millimeters of mercury. Because you'll know, okay, well, it's not 1 to 1. 1 atmosphere is not equal to 1 millimeter of mercury. So that's out of the question. And 22,000 seems a bit high when we've only got 2 atmospheres. So let me know, how did this one go? And also, as we work through, do you guys want the opportunity to try these, or are you looking for me to try them out for you first and just give you some more examples? Let me know what you're feeling today. We're a bit quiet today. Now we're going to get into the gas laws. The first law we'll cover is Boyle's law. His law looks at pressure and volume. This is Boyle's law. P1 V1 is equal to P2 V2, where P is the pressure and V is the volume. You have your initial pressure and volume, P1 and V1. Then you have your final pressure and volume, P2 and V2. Oftentimes in these questions, you'll be told about the initial conditions, and then one of those conditions changes. So, for example, you have a pressure of X, a volume of Y, and then something changes so that you now have a pressure of Q. What is the new volume? So you're given 3 of the 4 variables, and you need to solve to figure out what that 4th one is. Let's do one. We've got a sample of helium gas, and it has a volume of 120 milliliters. And a pressure of 850 millimeters of mercury. What is the new volume if the pressure is changed to 425 millimeters of mercury at constant temperature and moles? What you need to do with all of these problems, particularly on the exam and with your homework, is to identify the gas law that you need to solve it first. To do that, you look at all the information that you have. So I've got a volume and a pressure, and whenever you have those, a sample has this volume and this pressure, that's your initial. We've got 120 milliliters, 850 millimeters of mercury. What is the new volume? Well, the new volume is V2. We don't know what it is. If the pressure is changed to P2, 425 millimeters of mercury. When all you have is pressure and volume, that means Boyle's law. Pressure and volume are inversely related. What that means is, if the pressure increases, the volume will decrease. If the pressure decreases, the volume will increase. Here, we start with a pressure of 850. Our final pressure is 425. Did the pressure increase or decrease? Another way to ask that question is, P2, it's 425. Is that bigger or smaller than P1? It's a decrease. With Boyle's law, that means that our new volume should increase. When you do the math, that's what it should show. Now we can do some math. We said Boyle's law is P1 V1 is equal to P2 V2. We're trying to solve for the new volume, which is V2. Rearrange the equation. Divide both sides by P2. So you isolate V2 on one side and everything else on the other. Gather your pressures together. I'll show you why in a minute. Now we need to fill in everything from our given information from the problem. V1 is 120 milliliters. P1, 850 millimeters of mercury. P2, 425 millimeters of mercury. The pressure units cancel, and our answer is going to be in milliliters. Milliliters is a volume, so that's a good thing. That shows us that we solved the equation and we're getting the right units. Give that a shot in your calculator. You'll want to use parentheses here. That way you make sure that that division happens in the right order. Try it out and let me know what you get. Right, you should get 240 milliliters. Now this is a multiple choice question. We had 3 choices, 60, 120, and 240. We said that the pressure decreased, so the volume should increase. That means it couldn't be A, couldn't be B, had to be C. So we could have done this without doing any math. All you have to know is Boyle's law and how pressure and volume are related. But I always show the math just in case. You can check yourself. So for the remainder of this lecture, it seems like we're a little bit sluggish today, and that's all right. Semester is almost over. We got about a month left. A lot going on. Maybe you didn't get a chance to watch the video. I understand. So we're going to go through. I'll ask for some input here and there. Just let me know you're living. If you just need to kick back and watch, that's fine. And you can let me know that too. Like, Dr. Hefner, can you just show us? And I'll be like, all right. So that's Boyle's law. We've got another Boyle's law question. This one is a concept question, though. A sample of helium gas in a balloon has a volume of 6.4 liters at a pressure of 0.70 atmospheres. I'm going to start highlighting this stuff. At 1.4 atmospheres, is the new volume represented by A, B, or C? So let's break this question down. We've got a volume and a pressure. These are the initial conditions of the gas. We have another pressure. And we don't know what the new volume is going to be. Now, we don't need to do any calculations here, but we do need to use Boyle's law, the concept. Our pressure went from 0.7 to 1.4. Is that an increase or a decrease? It's an increase. So that's what that up arrow is. We increase the pressure. If we increase the pressure, the opposite has to happen to the volume. So what needs to happen to our volume? Is it going to be bigger or smaller than our initial? If the pressure increased, the opposite has to happen to the volume. So the volume has to decrease. If our initial balloon is here, which one of these balloons, A, B, or C, represents a decrease in volume? It's going to be A. A is smaller than the initial balloon, which is a smaller volume. Let me know if I should hold up here or if we're ready. We're going to keep pressing on. Please stop me if you have questions. The next law we're going to cover is Charles's law, and that's between temperature and volume. This is Charles's law, and what it says is that volume and temperature, they are directly related. If you increase the volume, you increase the temperature. If you decrease the volume, you decrease the temperature. And that is when you hold the amount of gas and the pressure of the gas constant. I'll show you how to use Charles's law. We've got a sample of oxygen gas. It has a volume of 420 milliliters and a temperature of 18 degrees Celsius. What temperature in Celsius will the volume of the oxygen be? 640 milliliters. And we're keeping pressure and amount of gas constant. You're not going to have the luxury of knowing what kind of question this is on the exam or on your homework. So you need to identify what pieces of information you have and match that up to a gas law. The initial conditions are always the ones with the subscript of 1. So if you have an initial volume, that's V1. And that's 420 milliliters. Temperature, T1, 18 degrees Celsius. We're asked about what the temperature will be. So we don't know that one. That's a question mark. But we know that the new volume is 640 milliliters. When all you have is volume and temperature, you're going to use Charles's law. Now let's just do a quick logic check. And I always do this before I get to my calculator. Temperature and volume are directly related. So if the temperature increases, volume increases. Temperature decreases, volume decreases. Here we're looking at the volume when we go from 420 to 640. That means that we have an increase in our volume. Since they're directly related, that translates to an increase in our temperature. So T2 should be bigger than T1. We can keep that in mind as we continue on with our problem. Oops. This is Charles's law, and as it stands, it's not really 100% helpful when we need to solve for something. The first thing that you need to do is cross multiply. So you're going to take V1 and multiply by T2, V2 multiply by T1. And what that looks like, I'll write it over here. That's after we've cross multiplied. Now we can solve for the variable we're interested in. We need to know what T2 is going to be. From here, it looks very much like Boyle's law in terms of solving. We divide both sides by V1. That way we have T2 on one side and everything else on the other. Collect your volumes all together like this. Now there's one more very important step before we can actually solve this problem. Whenever you're dealing with gas laws, you have to convert your temperatures to Kelvin. And the way you do that is you have to add 273. So Kelvin is equal to the degrees Celsius plus 273. I'll write what those are in red next to this temperature here. So that's going to be 291 Kelvin. The answer that we get back is going to also be in Kelvin. The question is asking for degrees Celsius, so we'll have to convert back to Celsius to find the correct answer. Now we're ready to substitute in our variables. T1 is 291 Kelvin. V2 is 640 milliliters. V1 is 420 milliliters. The milliliters cancel. Our answer is going to be Kelvin, which it should be because we're looking for a temperature. Now we can't stop here because our answer is in Kelvin. And you see letter A has 443 degrees Celsius. Don't be tricked by that one. You have to convert 443 Kelvin to Celsius. What that means is you're going to take your degrees Celsius, or to get degrees Celsius, you take Kelvin and subtract 273. So our answer is 170 degrees Celsius. Now we knew that the temperature should be bigger than our initial temperature, but that only allows us to cross off one of our options. So we had to do the math for this one. Are there any questions here? If not, at least let me know that you're here, you're with me, you're taking it in. Give me some feedback about where you are. Good. Much appreciated. Okay. Third gas law. This one is on temperature and pressure, and it's Gay-Lussac's law. This is Gay-Lussac's law. Looks pretty similar to Charles's law. It is pretty similar. As you increase the temperature of a gas at constant volume and you keep the same amount of gas, the pressure is also going to increase. That means that they are directly related. If you increase the pressure, then you're also increasing the temperature. Again, holding the volume constant and the amount of gas constant. Let's do a sample problem. A gas has a pressure of 645 torr at 128 degrees Celsius. What is the temperature in Celsius if the pressure increases to 824 torr and we're keeping the volume and the amount of gas constant? For every gas law problem, identify the pieces of information and then match that to a gas law. We've got an initial pressure, and an initial temperature. We're asked what the temperature will be in Celsius. So that's a question mark. But we know that our pressure increases to 824 torr, which is our P2 value. If all you see is pressures and temperatures for your given information, that's Gay-Lussac's law. Remember when we talked about the relationship, we said that there's a direct relationship between P1 and T1. We have an increase in pressure, 645 torr to 824 torr. That means we should expect an increase in temperature. So T2 should be higher than T1. Just like with Charles's law, we have to cross multiply to make this equation more usable. P1 times T2 and P2 times T1. Then you identify what variable you're solving for. And we need T2. To isolate it, you divide both sides by P1. I'm going to write my results up top here. T2 is equal to T1 times the ratio of P2 over P1. Remember to keep your variables together. So keep your pressures together, temperatures, volumes, group those together. Once again, we have a temperature in degrees Celsius. We can't use Celsius in gas laws. We're asked to give an answer in degrees Celsius, so we'll have to convert back after we do our calculation. When you add 273 to our Celsius temperature, T1, you get 401 Kelvin. That's the value we'll use in our equation. These gas law problems are not difficult, but you have to make sure that you keep an eye out for units and that you're putting P2 where P2 belongs and P1 where P1 belongs. So you must be organized, keep things neat. P2 is 824 torr. P1, 645 torr. I highly recommend writing out all the variables and assigning them numbers so that you can always check back. Our pressure units cancel. That means we're going to have Kelvin as the units for our answer. That's a good thing because we're looking for a temperature. When you do this math, you should get 512 Kelvin. But we have to report our answer in Celsius. So on your homework and on the exam, don't get trapped by that. Make sure that you do that last step to take your degrees, to take your Kelvin and convert to degrees Celsius. So there is our final answer, 239 degrees Celsius. Last check. We said T2 should be higher than T1. T1 is 128 degrees Celsius. T2 is 239 degrees Celsius. So it's definitely higher. That checks out, so it means our math is probably right. So there's an example of a Gay-Lussac's law problem. You only have pressures and temperatures, so you can solve for a final condition of temperature or pressure. Any questions here? So now we're going to go over a little bit of a concept because I want to make sure that you understand it. Vapor pressure and boiling point. These are they're related, but they're two different things. When you have a liquid in a container, an open container, let's say you have a cup of water. You drank some, you put it down, you walked away. I do that all the time. When the molecules on the surface of that water in the cup have enough energy, they'll break away and become a vapor. That means they, become a gas. Eventually, all of the liquid in that open container, my cup that I left on the kitchen counter, because I'm, drinking water while I'm cooking dinner for my family, it's going to be gone. It's going to evaporate. But if it's a closed container, if it's a fancy cup with a lid, that vapor is going to accumulate over the water, and it's going to create pressure. That pressure is called vapor pressure. At every given temperature, a liquid exerts its own vapor pressure in a closed container. It boils when the vapor pressure becomes equal to the external pressure. External pressure is another way of saying atmospheric pressure. At sea level, which is probably what you're at if you're here in North Carolina, our atmospheric pressure is 1 atmosphere. So when you're putting on that pot of water because you want to make some tea or you're making some pasta or something like that, it's going to boil when the vapor pressure equals 1 atmosphere. So I wanted to make sure to go over that one more time because that sometimes is a concept that's a little bit iffy. This is the take-home message. When your vapor pressure is equal to the external pressure, which in our case, we're talking about atmospheric pressure, your liquid will boil. At high altitudes, the atmospheric pressure is lower than 1 atmosphere. So the boiling point of water is actually going to be less than 100 degrees Celsius. So let's say you're in Denver, Colorado for some reason, and you want to boil water. The temperature that the water will boil at is slightly less because the atmospheric pressure is a little bit lower. But when you use a pressure cooker, like your Instant Pot, everybody's got an Instant Pot now, except me. I still haven't gotten one. You can actually achieve pressure greater than 1 atmosphere. So that means your water boils at a higher temperature. And that higher temperature is going to cook your food faster. And that's why it takes like 5 minutes for something to cook. So make sure that concept makes sense to you. High altitude means lower atmospheric pressure. And that's less than 1 atmosphere for us. That leads to the boiling point of water, which I'll abbreviate BP. It's less than 100 degrees Celsius. Make sure that concept makes sense to you. You'll see it as a conceptual question or two on your exam. And if you don't see it on the exam, it might show up on the final. So make sure you know it either way. I'm going to summarize the gas laws here, and then we'll take a brief break of about 5 minutes. If you don't want to take a break and you just want to go all the way through, that's fine. You can just let me know what you're thinking in the chat. If you want to take a short break after this, or if you want to just keep going, and when we end, we might end a little early. So the 3 gas laws that we covered so far. We've got Boyle's law, Charles's law, and Gay-Lussac's law. Charles's law, we're talking about pressures and volumes. When you increase the pressure, you decrease the volume, and vice versa. That's an inverse relationship. Charles's law, we're looking at temperatures and volumes. If you increase the volume, you'll also see a temperature increase. That is a direct relationship. Gay-Lussac's law, that's pressure and temperature. Increase the pressure, you'll also increase the temperature. And that is another direct relationship. But with these, we are making an assumption here. With Boyle's law, we're saying that temperature and N, which is the amount of gas, are constant. With Charles's law, we're keeping pressure and the amount of gas constant. Gay-Lussac's law, we're keeping volume and the amount of gas constant. And just so you know, N is moles of gas, which is our amount of gas. So this summarizes the 3 equations that we've gone over so far. It's great as a cheat sheet when you're doing your homework, when you're doing your quiz, and it'll help you study for the exam. This is a learning check that I wanted you guys to try. I'm still going to leave it blank here because I want you to try it on your own if you haven't already. I'll make sure that the answers are in here when I post the notes. So this, you're going to use the gas laws to complete each sentence with the word increase or decrease. This will help your understanding with the relationships between pressure, temperature, and volume. So I will fill this in before posting the notes to Blackboard. So let me know if you want to take a short break, like 5 minutes, or if you want to keep going. If y'all don't say anything, I'm going to just keep going. So let me know what you'd like to do. If you want to do something other than pressing forward and maybe getting out of class a little bit earlier, speak up now. Okay, we've got 1 vote for a break. So we'll take a short 5-minute break. We'll break until 3:25. Alrighty. Take a few extra seconds. But that's alright. It's 3:26. We're going to get back to it. The next gas law we have to cover is the combined gas law. This one comes from taking all the 3 gas laws that we learned, Boyle's law, Charles's law, and Gay-Lussac's law, and putting them together. And it relates all of the ways that pressure and volume are related, pressure and temperature, volume and temperature, in one equation. This is the combined gas law. It's the only one where you have all 3 of the variables we've been going over so far: pressure, volume, and temperature. Here, the only assumption that we make is that the amount of gas is constant. So we can change 2 properties of the gas and still figure out what the 3rd property will be. Let's do a sample problem. Again, I want to caution you here. Make sure that you're using the right units. Write out the units that you see in the problem. Make sure your units cancel, because now we've got 3 variables. 2 of them are changing. If there's temperature involved, you may have to do a conversion from Celsius to Kelvin. There can be a lot going on. A sample of helium gas has a volume of 0.180 liters. So what we're listing off now is all the initial conditions. Has a pressure of 0.8 atmospheres. Temperature of 29 degrees Celsius. What temperature in Celsius will the helium have a volume of 90 milliliters and a pressure of 3.20 atmospheres? And we're keeping N constant. That's a lot of stuff, all right? So let's write out what we know. The initial conditions of the gas, we have a volume, a pressure, and a temperature. In our final conditions, we're asked what the temperature will be. So we don't know that one yet. But we do know that we're looking for a volume of 90 milliliters and a pressure of 320 atmospheres. Oh, 3.2, not 320. That would be a completely different problem. Now I told you pay attention to units. For our initial volume, we have liters. For the final volume, we have milliliters. If we put this into the same equation, we would not get the right answer because liters and milliliters are two different units. So we have to convert one to the other. I'm going to choose to convert the milliliters to liters, but you could also do it the other way and still get the same answer, as long as the units are the same. So 90 milliliters that is 0.090 liters. If you're like, how did you do that? Go back to chapter 2 because you need to remember your conversions. Milli means 10 to the minus 3. Which is the same as 0.001. The other trick you might see is if the pressures are different units. So if I have atmospheres for P1 and millimeters of mercury or torr for P2, I'd have to do a pressure conversion so that they're in the same units. So in this problem, we've got a pressure, a volume, and a temperature, which means we have to use the combined gas law. We can't really do any predictions here in terms of what our temperature is going to be, because we've got two variables changing. We've got a change in our volume and a change in our pressure. They're both going to affect the temperature, but we don't know if it's going to cause an overall increase or overall decrease in our temperature. I'm going to write out the gas law in red. Just like with Charles's law and Gay-Lussac's law, we have to cross multiply first. So P1V1 times T2 and P2V2 times T1. Then you can isolate the variable that you're looking to solve for. We're trying to find T2. So we have to move everything else over to the other side. Divide by P1 times V1. You'll get T2 on one side multiplied by T1 times P2 over P1 times V2 over V1. Parentheses are your friend here. Make sure you use them. We're not quite ready to just plug in the numbers and go. Our temperature is in degrees Celsius. With these problems, it usually will be. You have to convert from Celsius to Kelvin. Add 273, and you get 302 Kelvin. That's the value that we use for T1. Let's fill it all in here. T1, we said, is 302 Kelvin. P1, 0.800 atmospheres. P2, 3.20 atmospheres. Now we're looking for V2, which again, we have to use the same units. So V2, I converted to liters. When you write out your equation this way, it's another way to double check and make sure that all of your units will cancel and give you the right unit at the end. So when you set up your problem and you're writing out your work, 1, write out your work, please. 2, write out the units. Don't just write numbers. Write units. That way you'll catch mistakes. Let's say you didn't convert one of your volumes so that they're different units. You'll say liters and milliliters. Wait a minute. Those are two different things. At least I hope that's what you'll say. And then you can do the conversion. So I take my time, I write these things out, not just to explain it to you, but because this method works. It helps you to take your time, put everything into the equation correctly, and catch any of those little mistakes that cost you a lot of points. These are multiple choice exams, and it's either right or wrong. So doing one little misstep will cause you the whole problem. Remember that. When you do all this math, you're going to end up getting a temperature in Kelvin. The question is asking for the temperature in Celsius. So we have to convert. We take our Kelvin temperature and subtract 273, and that gives us 331 degrees Celsius. That's our final answer. I'll pause here for a second, let you take it in. If you're taking notes, let you catch up a little bit, and then we'll move on. The next law that we're going to talk about, it is a gas law, but it's usually not, coupled in with the Gay-Lussac's law and Boyle's law and all of that. We're going to talk about Avogadro's law. Here we're looking at volume and moles. We're also going to talk about molar volume. So 1 mole of gas is equal to 22.4 liters. That's the concept of molar volume. In terms of Avogadro's law, we're relating the volume of the gas and the amount of gas. This is a direct relationship. If you increase the volume, then you're going to increase the amount of gas. And that is assuming that pressure and temperature are constant. So this is Avogadro's law. Direct relationship between volume and the amount of moles of gas. We represent that with an N. So let's use Avogadro's law. We've got 0.65 moles of helium and a volume of 2 liters. What volume will 1.2 moles of helium occupy at the same temperature and pressure? Just like with every single one of these, we write out what we know first and figure out which gas law we should use. So here's all of our information. If all you have is volume and moles, use Avogadro's law. Now, Avogadro may sound a little bit familiar. We talked about Avogadro's number in Chapter 7. Now we're talking about his law in Chapter 8. Cross multiply first. V1 times N2 and V2 times N1. We're trying to solve for V2. We get everything else away from V2. That means dividing by N1. Now that we have our equation, we can plug everything in. I also want to caution you here again, make sure that the volume is in the same units, liters and liters, or milliliters and milliliters. Whatever it is, it needs to be the same. V1 is 2 liters. N2 is 1.2 moles. N1, 0.65 mole. The moles cancel. We're left with liters. Let's do our logic to see where our answer should be. We went from 0.65 moles to 1.2 moles. That's an increase in the number of moles. That means we should have an increase in our volume. Looking at our answer choices, we can already say that one's not it. We will have to do the math on this one to figure out whether it's B or C. So you put it into your calculator. Remember to use your parentheses here. I didn't write them in. You should get B. So in a test situation, if you forgot how to use this equation, something happens, you can at least rule out one answer because it's not an increase in volume, simply because you remember it's a direct relationship. Don't just focus on the calculation. Remember to use your logic too. That can help eliminate answers so that you're not tempted to answer a wrong answer that goes against what you already know. That was Avogadro's law. Now we need to talk about molar volume. At standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, that's STP. 1 mole of a gas occupies a volume of 22.4 liters, and that is called molar volume. This is the equality. 1 mole of gas, any gas, doesn't matter of the identity. It could be oxygen gas, nitrogen gas, air, whatever gas it is. If it's at STP, 1 mole of gas equals 22.4 liters. With an equality, you get conversion factors. So you could put 1 mole of gas on top, the volume on the bottom, and then you can write the reciprocal. These won't change. If you have a gas at STP and you need to figure out volume, molar volume. Now let's do a check to show how to use this. How many grams of helium are present in 8 liters of gas at STP? Uh-oh. We're talking about grams? And I have liters. And we're talking about helium gas. This is going to cause you to go back to your Rolodex of things that you've learned, look through your notebook, and hopefully you'll look in chapter 7 because that's where you need to go to get the second part of this question. Right now, we have a volume. And we need to get to grams, which is a mass. Can't just jump straight there. But what we can do is go from volume to the number of moles, and then from moles to mass. To do this, volume to moles for a gas, only a gas, at STP, we use the molar volume. To get from moles to mass, that's something that we did in chapter 7. You need the molar mass of the gas. In this case, we're talking about helium. So beware. You can have a combination of chapter 7 and chapter 8 coming together to make a problem. For our first bit, molar volume, so this is the first leg of our equation. I'll write out the conversion factors. If we have 1 mole of helium at STP, we have 22.4 liters. And the reciprocal. Now we're going to try to go from moles to mass. We need the molar mass of helium. You go to the periodic table, you look at the atomic mass that's listed for helium. That's 4. You put grams after that, that's your molar mass. Now we can put our equation together. We're starting with 8 liters of helium gas. And we're going from liters to moles, moles to grams, which is mass. Get rid of liters, so we need to put liters in the bottom. We need to get rid of moles and replace it with grams. So for our second conversion factor, moles go in the bottom, grams go in the top. Make sure that we get the units that we're looking for. Then you do the calculation. 8 divided by 22.4 times 4. So there's our answer. The key to this problem is remember molar mass. That takes you from moles to mass and mass to moles. If you have questions, this is a good time, but I'm just going to keep pressing forward if nobody stops me. We've got a couple more sections to cover in Chapter 8. Ideal gas law. This law takes into account all of the properties of a gas: pressure, volume, temperature, and moles. So we know what P, V, N, and T are: pressure, volume, number of moles, temperature. Temperature is always in Kelvin. But the R, that's a gas constant. This is the only gas law that we have where we aren't talking about one condition and then we're changing some variables going to another. What we're saying is, I know 3 out of the 4 properties of my gas. What is the 4th one? We can use this to calculate volume, pressure, temperature, moles. If we use it to calculate moles, then we can also convert to mass. So we're going to again be combining ideal gas law, which is Chapter 8, with some Chapter 7 knowledge about mass and moles. But more on that gas constant first. When you're doing these problems, if your pressure is given to you in atmospheres, then you'll want to use this gas law constant. If your pressure is given to you in millimeters of mercury, then you need to use the constant that has millimeters of mercury. So be careful when you're doing your problems that you choose the ideal gas constant that has the correct pressure units. You do not need to memorize these. They'll be provided for you. Let's do a practice. Let's say that we need to figure out the pressure. I'm going to get my highlighter out here. What is the pressure? There's the question mark. In millimeters of mercury. That tells you which gas constant. Of 0.350 moles of this gas, which is laughing gas, N2O, at 22 degrees Celsius in a 5-liter container. whenever you're dealing with gas laws, write out what your information is and match it to the law. Our question word is along with the pressure. So we don't know what it is. But we know that we should answer in millimeters of mercury. So I'm going to write that there. Number of moles is N 0.350. We're given a temperature of 22 degrees Celsius. We'll have to convert this, so we may as well do it now. You add 273, and that gets you to 295 Kelvin. And last but not least, we're given a volume of 5 liters. Make sure that your volume is also in liters. The gas constants have the volume in liters. So if you're given milliliters, you need to convert. So make sure your volume is in liters and temperature is in Kelvin. Cannot use Celsius in gas law equations. When we have all 4 of our properties, that means ideal gas law. And we're asked about the pressure, we're told about moles, temperature, and volume. Ideal gas law. Now notice that I don't have R up here. We need to choose the right constant. The question is asking for the pressure in millimeters of mercury. So we need to use the R constant that has millimeters of mercury for the pressure. Now we've got everything except for the pressure. We can solve for that. Divide by V on both sides. Fill in everything you have for the problem. So the units for the gas constant, you've got units in the numerator and units in the denominator. So if you're writing out all of the units, you can write it out like I'm writing here, and it'll help you see how the units cancel. Moles cancel, Kelvin cancel, liters cancel. So the number we get is going to be in millimeters of mercury. You multiply all the numbers at the top, divide by 5. That gives you 1,290 millimeters of mercury. That's a sample problem with the ideal gas law. But it can get a little bit more complex than this. I'm not going to go through this one. This is the one that I solved in the video. So we're a little bit quiet. I don't want to go through this and then go through another problem. So if you want to see this one solved, see the YouTube video. Instead, I'll solve the next problem, which is like this. It's just got some different numbers. So you'll be able to see it solved again. We've got a reaction with nitrogen gas and hydrogen gas producing ammonia. How many liters of ammonia can be produced with these conditions? 0.850 atmospheres, 21 degrees Celsius, and we have a 6.50 gram sample of hydrogen gas and an excess of nitrogen gas. So this is combining Chapter 7 with the ideal gas law. We're given an amount in grams, a mass. And we need to first convert that to moles. Use a molar mass for that. We need the molar mass of hydrogen gas. To go from the moles of hydrogen gas to the moles of product, we can use a mole-mole ratio. Your book says mole-mole factor. Same thing. And that will get us the number of moles of ammonia. That's the first step. The second step is to use the ideal gas law. And that will take the number of moles along with the pressure and the temperature to figure out the volume. Let's do the first step. The molar mass of hydrogen gas, you look at the periodic table, you find hydrogen. What it says for the atomic mass, you multiply by 2. In the top, you're going to put 1 mole. That is our molar mass conversion factor. This will get us from mass to moles. Then we need a mole-mole factor, and that relates the number of moles of hydrogen gas to the number of moles of ammonia. You have to look at the chemical equation. We're trying to get rid of hydrogen gas, so the number of moles that we see in the chemical equation, we write on the bottom. We write the number of moles we see for the ammonia in the top. The goal is to go from grams of hydrogen gas to moles of hydrogen gas to moles of ammonia. We get to moles of hydrogen gas, moles of ammonia. Then you do the math. 6.50 divided by 2.016, and then you multiply that by 2/3. You should get 2.15 moles. But remember, that's moles of ammonia. The next step, we're going to use the ideal gas law. We're looking for the volume of ammonia that we produce. So we need to isolate that away from everything else. Divide both sides by P. Now let's see what our variables are from the problem. We solved for N, and that's 2.15 moles. T, we're told, is 21 degrees Celsius. But we always have to convert. So add 273 to that. (294 Kelvin). Our pressure was given to us in atmospheres. That means for our R value, you have to use the one that has atmospheres. Now we're ready to put all that information into our equation. Remember that the units for the gas constant, we've got a numerator and a denominator. And that is so that all of our units will cancel. Not going to talk about how the R constants were calculated, but when it's calculated, this is how the units work out. Then we go through and make sure that all of our units cancel. We've got moles canceling, Kelvin cancels, atmospheres cancel, and we're left with liters. Multiply everything at the top, divide by 0.85. We make 61.1 liters of ammonia gas and in these conditions from 6.50 grams of hydrogen gas. This is probably the most involved problem that you'll have from this chapter. If you didn't have a problem with chapter 7, then this should be pretty smooth. If chapter 7 was a little iffy, then you'll definitely want to practice this type of problem. The final segment for today, we're going to talk about partial pressure. This is also called Dalton's law. The idea is that if you have a mixture of gases, then the total pressure of the mixture is going to be equal to the partial pressures of all the individual gases. So that's the total pressure, P sub T. And you have all these other smaller pressures that are the partial pressures of the different gases in the mixture. I'll show you how we use that. Oh, I have this nice slide too. So this demonstrates the idea of a mixture of a gas. If I mix helium and argon together, and I've got 2 atmospheres of helium and 4 atmospheres of argon, I'm going to add those 2 pressures together to get my total pressure. And that's 6 atmospheres. Doesn't matter what units you have, atmospheres, millimeters of mercury, whatever. You can add them together. Let's do a learning check. I talked about scuba diving a little bit in the pre-recorded lecture. And when you go scuba diving, you need oxygen. You can't just breathe water. You're not a fish. You can't remove the oxygen from the water and use that in your metabolism. If you can, you're amazing. But for everybody else who decides to go scuba diving, not me, you have to use oxygen. And it's not just pure oxygen. It's a mixture. So you'll see helium and oxygen, or sometimes you'll see nitrogen added. Either way, you need to have an oxygen tank of some kind when you go underwater. This particular scuba diver in our question uses a mixture of helium and oxygen. And it has a pressure of 6 atmospheres. That's the total pressure. If the oxygen has a partial pressure of 975 millimeters of mercury, what is the partial pressure of helium? And we're assuming that the volume and the temperature are constant. Not a difficult problem. We already know that the total pressure is going to be equal to the pressure of the helium plus the pressure of the oxygen gas. We know that the total pressure is 6 atmospheres. We know that the partial pressure of the oxygen is 975 millimeters of mercury. You should see we've got a slight conundrum. Atmospheres and millimeters of mercury. We can equate them, but we've got to convert one to the other. And since all of our answers are in millimeters of mercury, it makes sense to convert the atmospheres to millimeters of mercury first. That's the only real trick with this problem. Make sure that your pressure units are all the same. Just like we did at the very beginning of class, you have to use this equality. 1 atmosphere is equal to 760 millimeters of mercury. You'll be provided with the different conversions. It won't necessarily be written as an equality, but you'll know all of these. You don't have to memorize it. We want to get rid of atmospheres, so that should go on the bottom of our conversion factor. 760 millimeters of mercury should go on the top. You multiply 6 by 760. Oops, I wrote atmospheres instead of millimeters of mercury. My bad. You see how the units cancel? But we're not done yet. This is the total pressure. We need to figure out what the partial pressure is for the helium. Our partial pressure for helium is equal to the total pressure of the mixture minus the partial pressure for oxygen. So all we did was rearrange that equation for Dalton's law to solve for the partial pressure of helium. So you'll get 3585 when you do the subtraction. But with sig figs, it's 3590. Again, the key to this problem, making sure that you, one, assign the variables properly. The 6 atmospheres is the total pressure, 975 millimeters of mercury, partial pressure of oxygen. Convert atmospheres to millimeters of mercury. And then you can solve. Here's your reminders for this week. You've got an exam. It'll be available right after this class. And you have until the very end of Saturday to start it, 11:59 p.m. Multiple choice. Just like usual. Then you've got your Chapter 8 check-in and Mastering Chemistry due. That's due on Wednesday, April 7th. The chapter check-in for Chapter 8 has been up for a while. Make sure you get it done by Wednesday of next week. Submit it on Blackboard as a PDF. If you have any questions, you can ask them now. Otherwise, you're free to go.